This is the first of a sequence of video lectures on linear algebra that is based on the book by Rao and Bhim, second edition. The first comment that I want to make about the book is that this is a very bad book, a very badly written book with emphasis given on the wrong things, and one cannot form a healthy concept about the subject by reading this rubbish. There are plenty of good books available on the topic, and one book which I like particularly well is by Stephen Leon, and another book is by Gilbert Strang. And I would strongly advise anyone who tries to learn linear algebra to follow either this book, which is somewhat easier, or this book, which is more comprehensive. And this book is also accompanied by video lectures by the author himself given in MIT. The only reason I am making these video lectures is because in certain institutes, certain teachers follow this very bad book and students have to suffer a lot. So I am trying to make their life a little less difficult. Chapter 5, Linear Equations. In this chapter, we discuss such things: system of linear equations. We have a number of unknowns, x1, x2, in this case 2 unknowns. We have got 3 equations. No product of unknowns or no square of unknowns are allowed, hence we call them linear equations. Such a system of equation may be conveniently written in the form of matrix. So this is the coefficient matrix. These numbers are obtained from the coefficients. This is the vector of unknown, and this is the right hand side, a vector of constants. The general form is Ax equal to b, where A is the coefficient matrix, x is the vector of unknown numbers, and b is the right hand side, in this case this. And m is the number of equations, in our example 3, n is the number of variables or unknowns, in our example that is 2. If I expand out this matrix equation in general form, I can write it in this way. Just observe that the ijth entry of A is written as Aij. The first index denotes the row, which means which equation it is part of, and the second index denotes the column, that is which unknown variable it is the coefficient of. So if I have Aij here, then that is the coefficient of xj in the ith equation. Definition 5.1.1 introduces 4 terms. The first one is consistent. By a consistent equation, we understand an equation which has got at least one solution. This is an example of a consistent equation because I can find numbers x1 and x2 such that their sum is equal to 10. For example, I can take this to be 2 and this to be 8. A system is called inconsistent if it has got no possible solution. For example, if with it I add another equation 2x1 plus 2x2 equal to 11, that will be an inconsistent system because both these two things cannot be satisfied simultaneously. If x1 plus x2 is 10, 2x1 plus 2x2 must be 20 and not 11. This system is an example of an inconsistent system. A system is called homogeneous if this right hand side B is just the 0 vector. Then we call it homogeneous. If this right hand side is something which is non-zero, that is at least one entry of B is non-zero, then we call it a non-homogeneous system. This is an example of a homogeneous system because all these numbers are 0. If at least one of them is non-zero, then this system is an example of a non-homogeneous system. Next, the book defines two other terminology. First is general solution. By general solution of a system, we understand the set of all possible solutions of a system. For example, if I have this system, in that case, it has got many possible solutions. I can see that 2, 8 is a solution, that is x1 is 2 and x2 is 8. Similarly, 20 and minus 10 is also another solution. So the general solution will be this set a and 10 minus a, where a is any real number. That is the general solution of this system of equation. By a particular solution, we understand any element of this set. For example, this is a particular solution, this is another particular solution. Every element of the set, which is general solution, is called a particular solution. Section 5.2 discusses only homogeneous systems, that is, systems of the form Ax equal to 0. Such a system is obviously always consistent because one solution is always given by x is equal to 0. This solution is also called the trivial solution of this system. If x is not equal to 0, any such solution is called a non-trivial solution of the system. Here is an example of a system with a non-trivial solution. Suppose I have 2x1 plus x2 equal to 0 and 4x1 plus 2x2 equal to 0. You can easily see that actually I have only one equation here, because this is nothing but twice that equation. So whenever I take any x2 and I take x1 to be just its half with a minus sign, I'll have a solution. So I can take x1 equal to 1 and x2 equal to minus 2. That will be an example of a non-trivial solution. In what follows, the book will now try to find answer to the question, when does a homogeneous system of equation have non-trivial solutions? For this, it will help us to remember certain facts about vectors which are not mentioned in this chapter. The first is, when I write Ax equal to b, I am basically saying that b is a linear combination of the columns of A. Think of A as a collection of columns. In my example, I have taken 3 columns and x consists of 3 numbers. In that case, when you do the matrix multiplication, it is same as multiplying this column by this number, the second column by the second number, and the third column by the third number, and that linear combination is actually equal to the right hand side. You might like to do the computation yourself with this example. This is nothing but 100 times 1, 2, 3 plus 1 times 4, 5, 6. So just do the computation. You can see that this is actually a linear combination of these 2 columns with these as the coefficients. In view of this, we can say that this being consistent is equivalent to saying B belongs to the column space of A. This equivalence is very important to keep in mind. The book does discuss this, but only a bit later. The second point to remember starts with this obvious notation that if V belongs to span of some u1 to un, we mean by this that V can be written as a linear combination of ui's with some scalar coefficient ci's. However, if we have an extra condition on u1 to un, namely that they are linearly independent, then we have some extra condition automatically on the CIs, namely the CIs must be unique. So anything inside the span can be written in one and only one way as a linear combination of the UIs. The proof of this is not at all difficult, but since I am following the flow of the book, I will just use it as a result, because this result is going to be used pretty soon. Theorem 5.2.1 says that a homogeneous system of equations, which has got n columns, that is n unknowns, has a non-trivial solution if and only if the rank of the matrix A is strictly less than its number of columns. The proof is pretty straightforward, because if you remember that this simply says 0 can be written as a linear combination of the columns of A, and at least one xi is non-zero here because we are working with a non-trivial solution, then from the very definition of linear independence we can say that these columns must not be linearly independent. That is, the rank of A must be less than the number of columns that we have, and that is n. And conversely, if rank of A is indeed less than n, then they are not all linearly independent, and since they are not linearly independent, I can find some linear combination of them with at least one of them non-zero, such that the linear combination equals the zero matrix. By collecting all those xi's, I form my non-trivial solution, and that's the proof. Theorem 5.2.2, if we have a homogeneous system of equations, then the set of all solutions forms a subspace of Rn. The book says Fn because it is working with general field, but just to fix ideas, I am using real numbers, Rn. And this subspace has dimension n minus rank of A, where n is the number of columns. This statement combines two things. One is little more than a very trivial check, namely that the solutions form a subspace. So all that I have to do is to check that if I have any two solutions, call them x1, so this is a vector, and x2 another vector, and I form any arbitrary linear combination of them, A plus B times these are scalars, then this will also be a solution, which is very trivial to check. A times this, I need to show that this will also be equal to 0, and that is little a times capital AX1 plus little b capital AX2. Because I have started by assuming that AX1 or x1 and x2 are solutions of this, so this is 0 and this is 0, so the entire thing is 0. So I have shown that the set of all solutions is closed under arbitrary linear combinations, which in its turn implies that this is a subspace. The second part of the theorem is quite non-trivial, but first let me comment that this subspace is what we call the null space of A, or the kernel of A. That is just a notation, and the fact that its dimension is n minus rank of A is a pretty non-trivial fact. In fact, Gilbert Strang says that this is the fundamental theorem of linear algebra, and I am not going to prove it here. In the book, they refer to something else beforehand. I will refer to my video where I have discussed rank. So I had sent two videos. The second video will have a detailed proof of this fact. So this is a non-trivial fact. Example 5.2.3. Here the book tries to give you a method by which you can compute the general solution of any homogeneous system of equations. But because of the bad way of writing, the way they are presenting is neither general nor clear. So what I shall do is, I shall first give you a really general way of finding the general solution, which works even for non-homogeneous systems. and then I will explain what the book is trying to do. Now, the general technique that I was mentioning is just this: try to keep on eliminating variables, that is expressing the unknowns in terms of the other unknowns until you cannot go any further. So let's try. We can do it starting from the first equation like that, but since we are looking at it with our human eye, so I can see that the second equation is the simplest in the sense it has got the least number of variables. So I will write this x4 in terms of x1 plus 3x3. So I will write it as x4 equal to minus half x1 plus 3x2. And similarly, by the second equation, I can see that I already have x4 written in terms of x1 and x2. So I have only got x3. So from that, I shall get in a similar way half of x1 plus 3x2. So as long as I put these x3 and x4, I am guaranteed that these two equations will be satisfied. So in order to learn something about x1 and x2, I should put all those things in the first equation. And if you put them in the first equation, you will get 0 equal to 0, which means the first equation brings no extra information. It is just formed by taking linear combinations of the last two equations. So I get my general solution. The general solution is any x1, x2, x3, x4, where x3 and x4 may be expressed in terms of x1 and x2 like this. This we shall write in the form of vectors. Like this. x1, x2, x3, x4 is completely written in terms of x1 and x2, and x1 and x2 are perfectly arbitrary. So I have x1 is just x1, so no contribution of x2 there. x2 is just x2, no contribution of x1 there. But x3 is made up of x1 and x2, so I have got x3 is half and 3 by 2 x2. Similarly, x4 is minus half and minus 3 by 2 x2. So I can see that the general solution, that is the null space of the coefficient matrix, is made up of all linear combinations of these two vectors. So they constitute a basis for the null space of the coefficient matrix. So that is one way of obtaining the general solution. Now I shall describe the method that is given in the book. That method starts by first extracting the coefficient matrix, this 2, 1, 1, 6, 3, 3, 1, 0, minus 1, etc. and then observing that a basis of the column space consists of the first column and the third column. You can easily see that this is 3 times that, so this brings the fresh contribution. And if you add twice of this with this, then you will get the last column. So this is based on completely on inspection, and that's why I hate this book. You cannot even know how to do it in general. So they are saying here is a method to find the general solution, but this is completely by inspection. Okay, so you can see that the first column, leave it like that, and the second column is twice the first column. So if I call the first column A1 and A2 and A3 and A4, then A2 is actually twice A1 and A3 is one of the basis things. So A4 is thrice A1 plus A3. So you have this particular relationship. Now from this we can get certain linear combinations of the columns which are equal to 0. For example, I can see just by rearranging these things that minus 3A1 plus A2 plus 0A3 plus 0A4, this is equal to 0. Similarly, from this one I can see minus 2A1 And well, I will write is plus, then 0a2 plus a3 minus a4 is equal to 0. Now a linear combination of the columns of A, that can be written as A times x. So here the coefficients are minus 3, 1, 0, 0, which means if I write minus 3, 1, 0, 0, then I will get the 0 vector. In other words, I have obtained one vector in the null space. Similarly, if I use these as my coefficients, then I will get another linear combination which is 2, 0, 1, minus 1. Then that will give me another linear combination, will give me another vector in the null space of A. Now here the book takes a leap of faith, and the leap of faith is the following. These two relations that we got were obtained separately. You cannot derive one relation from the other, so they must be linearly independent. And also these are all the linear dependents that you can get. These are all the relations that you can get among the columns of A, which will give you 0. From this they conclude that these two things constitute a basis of the null space of A. This requires quite a bit of proof. It is true, because in this case we do not see any further relationship between the columns. So these are all the relationships that are there. Every other relationship must be generated out of them. So these two vectors generate the null space, and one cannot be obtained from the other, so they are linearly independent. But the book just takes a leap of faith and directly says, hence we can see that these two forms a basis. And now you can write down the general solution in this way: any arbitrary linear combination of these plus arbitrary linear combination of this. Now the same set, same general solution may be couched in different forms which will look different. The book gives you yet another form, and we have already seen one form. So there are lots of different forms that you can get for the same general solution. So that finishes section 5.2.